Hey, my name is Arjun Verma, and this is my 5th lab about Faraday's Law. So this lab is about exploring Faraday's Law and how it relates magnetic field to electric field and EMF. You can see it on the right, with EMF being equal to the number of turns times the derivative of flux. We'll utilize a magnet, along with some other accessible items, such as a smartphone, to conduct a real-world experiment to explore how Faraday's Law works in real life. We'll model and see how it works, as well as how magnetic force works. So first, the process of the experiment. So I followed the setup described in the lab with the magnet in the tube and my smartphone beneath to measure the field. It was a pretty fun way to interact with the lab, and on the right you can see like some demo of this. It's the tube around it, the magnet going down, the magnetic force acting against it, gravity pushing it down, and F net would be down because it will fall. So the quick question, a ferrous tube would be magnetic and its field would interfere too heavily with the experiment, therefore we cannot use one. So yeah, as for the results and the data, the first part of this is the basics. So the width of the tube was 5.8 centimeters, the length was 31, the radius was 4.1 overall, and the magnet's mass was 35 grams. And the results of the experiment, we found that the average time across 5 trials of dropping the magnet was 0.73 seconds for the magnet to drop all the way through the tube. So for the checkpoint question again, the magnet is slowed down by the effects of the field forces of the interactions with the tube, so it would fall faster in free space because there wouldn't be any magnetic force acting against it. Yep. So yeah, now going into the modeling of the experiment in real life. So on the left over here, you can see I input all of the parameters that I described earlier, like the length of the tube, the width, the inner radius, and the radius, as well as everything else. So this is the initialization of everything. And then after that, these are the formulas for calculating the actual magnetic field and the magnetic flux to determine force and EMF and everything else that would be relevant. So these are my two main defined functions to do that, right? And it just follows the same formula as was given to calculate these things, except in our specific situation. So as for the results, you can see this is at the very end. This is the magnet going all the way through the tube with the blue and red representing currents. And on the bottom, you can see the velocity versus time graph. It shoots down pretty sharply and then remains consistent, then shoots down sharply again. And I found that our experimental time in the tube was 0.69 seconds, or 690 milliseconds. So interpretation of the modeling and simulation, right? There's a lot of different things we can interpret. So for the first part, we can deduce that the red color means counterclockwise current and the blue one means clockwise through our specific application of Lenz's law in this situation. And if we were to flip the magnet, nothing would change except for the direction of the currents, right? Because the dipole direction would change, so the direction of the current would change. My real-world system takes more time than my actual experimental system, and this may be due to factors such as human error. So I could have made error in starting and stopping the recording, or where I dropped the magnet from exactly, or maybe if I put a little less force on the magnet or something like that. And as well as this, there could be other factors that I didn't calculate, such as air resistance, acting against the magnet and making it come down slower than it would have without air resistance in my simulation situation. And the shape of the velocity versus time graph, i.e. how it increased in magnitude in the negative direction, then stopped, shows us that the initial force on the bar was strong and then petered out as the velocity became constant. So now for the what-ifs. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the flying magnet change? So if the resistivity was reduced as close as possible to zero, then the current in the conductor would have been larger, right? Because of the V equals IR rule, and because the voltage would have been consistent with the previous experiment. So the current would be a lot stronger, and the force might be increased more, or it could potentially be decreased by having a higher current and have the magnet come down a little bit slower, right? And then also, if there are holes or slots cut into the tube, how this affect the ring currents in our model. So the current through the tube would not be as consistent because there would be holes throughout the tube, so there wouldn't be as big of a collection of electrons and current through there. So it would be less consistent, and the actual magnetic field generated would be weaker. Therefore, the braking force would not be as strong, and the magnet will come down a lot faster. And that has a lot of implications for other parts of our lab, because the magnet wasn't coming down as fast, then our graph would change, our calculations for B field would change, and our calculations for force would change. So that definitely changes a lot about our lab, and it kind of shows how having this specific setup is very important to the lab itself, and how you need a specific setup to explore lenses and Faraday's law in real life. Yeah, these are my references for the lab itself and whatever images I used. Thank you guys so much. I really enjoyed doing this lab and seeing how the magnet interacted with real life. Thank you.